We start with a couple of definitions. These are definitions of local extrema. We have local maximum and local minimum. We say that a function has a local maximum at an x value, x equals c1, if it's the highest point nearby. And so we see this graphically right here. This is the highest point nearby. And by nearby, I mean if we're restricting our view only to that general area, that's as high as it gets. It's a mountain. But certainly if we look at the whole function, we see points that would be higher because we've got this upward arrow here on the right-hand side. So we do have higher points. But that doesn't really matter because when we're talking about local maximum, we're talking about just locally, nearby. And we can have the same sort of definition for local minimum. We say a function has a local minimum at an x value, let's say x equals c2, if it's the lowest nearby. And so these are like our valley points. And certainly if we look at the function as a whole, since we've got the downward arrow on the left-hand side, we've got lower points over here. But it doesn't really matter because if we restrict our vision to nearby the x value, x equals c2, those are the lowest point occurs at c2. And so these again are called local extrema. We could formalize this definition using math terms and math symbols, but really to get the idea across, you can really just think about this sort of picture here. So comparing a couple of different graphs that have local maximum and local minimum values, we see the first graph, the one on the left, is just a copy of the one from the previous slide. We have the C1 where we have our local max here at C1. Let's see, we'll say local max. Because it would be the highest points nearby, and we've got the local min here at C2. And we notice here that in each one of these we've got a nice smooth function and we have a horizontal tangent line at that local max and the local min. But it's not necessary that the function's smooth. We can still have local maxes and local mins at places that are sharp turns, corner points. And so we do have a local max here at our peak or sharp peak, and we have a local min here at our sharp valley. And so the difference between these two graphs is this first graph, the one on the left, we have f prime of c1 is equal to 0 as well as f prime of c2. Both of those are 0 because we have horizontal tangent lines at both of those points. The graph is nice and smooth there. But then in comparison for our second graph, the one on the right, we have that f prime of c1 is undefined. And same goes for f prime of c2. That would be undefined. We can't define a tangent line there because if we look from the left and the right, the tangent lines would be different slopes. So the nice difference quotient limit does not exist because the left limit and the right limit don't match. And so we have there that the derivative at those two corner points would be undefined. And so the comparison of these two graphs is really motivation for our next definition, and that's a critical point. So we say that the x value c is a critical point of f of x if two things are true. So the first thing that has to be true is we have to have that x equals c as a point in the domain. So we have x equals c is in the domain of f of x. Okay. And what it means for an x value to be in the domain is that you can plug that x value into the function f of x and nothing bad happens. It's an allowable point. It's not a missing point, a hole, or you don't have a vertical asymptote or anything like that. It's a point that you can plug into the function, a point that would be on the graph. An x value that when you plug it into the function gives you a point on the graph. So the other condition is coming from really our motivating pictures. Not only does that x value need to be in the domain, we need to have the derivative evaluated at c, so that f prime of c, that's either going to be 0 or it could be undefined. that's where our critical points are. Interesting things happen where, or at c values where, or x values, where the derivative is either 0 or undefined. But graphically, sometimes we can have a critical point and nothing particularly interesting as far as a local extrema is happening. And so what I want to do next is look at the two scenarios. The top row is where the derivative is equal to 0, and the bottom row is where the derivative is going to be undefined. And so I just want to give you kind of a quick visual of what such a local max, local min would look like for each, but moreover, what would be the sort of graphical thing you would see if it's a critical point, but it's neither a local max or a min. So when we're talking about the derivative being equal to 0, we're really talking about the curve being smooth. And so if we're talking about a local max, it really is a nice smooth mountain, because there at the peak we would have a nice tangent line that would be the derivative equal to 0. For the local min, it would be a nice smooth valley, where at that lowest point there we have the horizontal tangent line again, because that would be the derivative equal to 0, and locally that's the smallest value. So now in comparison, we want to have a place where the derivative is 0, but it's not a max or a min. And so we do need a horizontal tangent still, but it can't be a peak or a valley. And so that would be something like this, where this turning point here has a horizontal tangent, but the function itself is continuing to go up. So this might look like something like x cubed, y equals x cubed. So now in comparison, when we're talking about the derivative being undefined, times where we had the derivative undefined were either sharp turns or cusps. We could also have vertical tangent lines, or perhaps discontinuities, but see, we're not working with discontinuities for critical points because we're talking about domain points only. So let's look at what a local max would be if the derivative was undefined. So perhaps we would have a sharp turn like we saw kind of in our example graph, or even we can make it a cusp where we have a local max there, but it's making a sharp turn. We could do the same sort of thing with just the reflection for the local min, where we have a sharp turn or a sharp cusp to get a local min. Each time that local max and the local min had derivative undefined because we made a sharp turn there. But we do see the local max and the local min respectively there. Now, how we can get a graph that the derivative is undefined but is neither a max or a min, the thing I usually think about is something that would have a vertical tangent line, because vertical tangent lines mean the derivative doesn't exist. But so we've got now a case where we've got a vertical tangent line, but we don't have a peak or a valley because the whole function is just continuing to go up.